Welcome to the Deep Dive. Today we're taking you into a really unique intersection of technology and climate.
Right, specifically looking at Denver, Colorado.
Exactly. How Denver is approaching energy generation, not just banking on sunshine, but interestingly also from rain.
It sounds a bit futuristic, doesn't it? Sun and rain power together.
It really does. Our mission here is to unpack these innovative systems they're starting to use. We've got some great sources, including a white paper from Black Knight Power that details these hybrid solar rain setups.
And it's fascinating how they tackle the classic solar problem. What happens when it's cloudy or raining? Suddenly, that's not just downtime, it's another energy source.
Let's set the scene a bit. Denver's climate is, well, it's known for sun, right? Over 245 sunny days a year, generally.
Fantastic for solar, you'd think. But there's a catch. They also get pretty variable precipitation and sometimes significant hailstorms.
Okay, so that's the problem. Your standard solar panels, they take a hit during storms.
They do. Efficiency can drop somewhere between 10 to 25% when the clouds roll in or it's raining heavily. Less light gets through, it impacts consistent output.
So you can't just rely on the sunniest days. You need something more resilient.
Precisely. And that's where these hybrid solar rain systems come into play.
Okay, let's get into the science. How on earth do you get electricity from a raindrop? Seems like a tiny amount of energy.
Well, it is tiny per drop, but it adds up. The key technology here is something called Triboelectric nanogenerators, or TAM.
Tayangs.
Yeah. They basically convert the kinetic energy, the movement of raindrops hitting a surface, into electricity. It works through liquid-solid contact, generating a charge.
Huh. And how much power are we talking about?
This is the surprising part. Research shows they can generate up to 2.14 volts from a single droplet impact.
Whoa, okay. 2.14 volts. That's actually quite a bit from one drop. More than a day battery, isn't it?
Exactly. It demonstrates there's real potential there. So the idea is you layer these TANs right onto the solar panels.
So the panel works when it's sunny, and the tenning layer works when it's raining.
That's the concept. Continuous energy production, smoothing out those weather-related dips.
But solar panels and water, historically not always the best mix. And then there's hail. How do these hybrid panels hold up?
Good point. This is where material science comes in. They often use perovskite solar cells in these setups.
Perovskites, okay. Why those?
Well, they're known for really high sunlight to energy conversion, potentially up to 93% efficient in converting photons. And crucially, they can be engineered to be more resistant to water damage than some traditional silicon cells.
And the hail.
Right, Denver's famous hail. They use protective coatings like fluorinated carbon coatings. Tests show these help panels maintain about 80% efficiency even after extended exposure to humidity.
And for direct impacts.
There was a study by NREL, the National Renewable Energy Lab, actually based near Denver. After a really severe hailstorm, they found only about 1 in 3,000 panels sustained significant damage.
Wow, that's incredibly durable. Much better than I would have guessed.
Yeah, it shows that engineering is really addressing these challenges. So you put it all together, the perovskite cell for sun, the 10 layer for rain, the protective coatings.
And the 10 part, how much does it realistically add?
During wet periods, for something like a standard 6 kilowatt residential hybrid array, the energy from raindrops might contribute around, say, 5 to 10% of the total output. Not massive, but it's extra power you wouldn't otherwise get.
Okay, so this isn't just theory. You mentioned Denver Water is actually doing this.
Absolutely. They have a big 929 kilowatt system using solar canopies over parking areas.
Parking canopies make sense. Dual use.
Right. And that garage canopy alone offsets about 30% of that facility's energy use. Plus, and this is really important in Colorado, it's designed to channel stormwater for reuse.
Ah, water conservation too.
Yes, they estimate it reduces water evaporation losses from the area it covers by about 15%.
That's clever. What else is happening?
There's also the concept of photovoltaics, basically floating solar arrays on reservoirs.
Floating solar. Okay, tell me more.
The potential in Colorado is huge. They've identified maybe 1,900 suitable reservoirs. If arrays were deployed there, estimates suggest they could prevent, get this, 429,000 acre-feet of water evaporating annually.
Wow. How much water is that in context?
That's actually more than the entire city of Denver uses municipally in a year.
That is staggering. So it's energy and massive water savings. Is anyone doing it yet?
Yes, there are smaller examples, like a 200-panel floating system in Walden, Colorado. It's proving the concept.
And what about making sure everyday people benefit? Community solar.
Definitely part of the picture. Denver has initiatives like the one at the Montbello Recreation Center. It's a community solar garden where about 35% of the energy generated is allocated to help low-income households reduce their electricity bills.
That's great to see tying renewables to community benefits. But let's talk challenges. You mentioned T&Es. Are there hurdles in making them bigger, more effective?
There have been technical challenges, yeah, particularly with scaling them up, issues around coupling capacitance affecting efficiency, but research is ongoing. Tsinghua University, for example, optimized some 10 configurations and got like a 385% boost in peak power output compared to older designs.
Okay, so progress is being made. What about the cost? Adding rain harvesting can't be free.
No, it adds cost. Right now, a standard solar install in Denver might average around $2.28 per watt. For a typical 6 kilowatt system after the federal tax credit, you're looking at maybe $9,500 or so.
And the hybrid rain solar version.
It adds an extra maybe $1,500 to $2,000 upfront to that 6 kilowatt system cost, so it is more expensive initially.
But does it pay off?
The argument is yes, because it generates power more consistently, even in bad weather. This tends to shorten the payback period by roughly 2 to 3 years compared to a solar-only system. Plus, Colorado has a renewable energy standard pushing utilities, and Denver itself offers local rebates, sometimes around $1,000 per kilowatt.
So incentives help bridge that gap. Looking ahead then, what's next? Where does this technology go?
We're seeing advancements in material science, things like using AI models for real-time fault detection in panels. They're claiming like 95% accuracy, and developing graphene-enhanced TENS that might capture 20% more energy from raindrops.
Interesting. And connecting it all to the grid.
Smart grid integration is key. Xcel Energy, the utility there, is piloting things like time of use rates, which encourage energy use when renewables are abundant. And there are AI platforms being developed to optimize panel angles automatically, potentially boosting annual output by another 12%.
And policy, what needs to happen there?
There's definitely advocacy around expanding things like community solar incentives to specifically include rain harvesting features, maybe even targeted tax exemptions for 10 components to bring costs down further.
So bringing this all together, what's the main takeaway for our listeners from Denver's approach?
I think Denver really shows how you can take climate variability, something often seen as a negative for solar, and actually turn it into an advantage by innovating. Using technologies like TENGs and perovskites isn't just about watts, it's tied into water saving and, importantly, energy equity through community projects.
Yeah, it paints a picture of a more resilient and, well, rounded approach to sustainable energy. This deep dive certainly shows that with the right mix of technology, policy, and maybe a bit of creative thinking, cities can adapt.
Definitely. It moves beyond just relying on sunshine.
It really makes you think, doesn't it? Could your city be next to turn its rainy days into a power source?